Hey, Titus Dudden here for CpE 3110 Project 3. I'm making this little intro recording just because I recorded the circuits a bit out of order. So this is just a little introduction as to what these circuits are a part of. Once again, CpE 3110 Project 3. Okay, for this circuit, this is our complex logic or sparse computer circuit that we're doing here. So this is going to be pretty complicated, so going to be a bit lengthy. So we have two values that are both 4 bits, so 0 and 1, and then imagine a decimal between 0 and -1, and then there will be the -2 after that. So we have two complex numbers with a real part and an imaginary part, and then we have our real and imaginary output, some observation states. Pretty much all of these are observation, so you'll see those in the waveform. Here we have our clock, our reset, our start. Again, more observations here. These are our control signals for all of our registers and our adder. These wires here are, again, most of these are going to end up becoming observations, just so that I can actually track where the data is going throughout the test bench. Here we have the states, and down here we have the assignments, which there are a ton because there are a ton of I've said the word too many times, I lost it. Observation outputs. So like all of these are control observations. These are the assignments for the muxes. So it's saying that the P operand, the Q operand, and then the Q2 operand. And then down here we have, again, more observations for the selectors. Here, this is the mux and the mux output so that I can see what I'm actually looking at. Down here we have the, this is the adder logic, which the adder logic is a little convoluted because while programming this, I realized that the adder needs to be able to do different things based on what step it's doing. So I had to, and just to keep the timing, to actually work properly and not have any disconnects between the always blocks, I just made it outside the always block. So it's just a bunch of if else's inside if else's. And then again, another observation. Down here, these are the partial product registers and then the endpoint registers. This is just saying if it's reset, it's set to 0, and if it's high, then it'll take in the value. Down here we have the state register here, which is just determining how the next state is calculated, and again, an observation. Here is the next state logic, which is just pretty much explaining that if the start does not go high and we're in step 1, it stays in step 1, resets high, stay in step 1, else it moves on to step 2, and then it just keeps going down the line. After this, we have the output logic, which is just setting everything to 0 initially, and then setting our values per step. So nothing, this part isn't too bad. Everything else, a little crazy. And then I did have to add a buffer state because it would switch to step 1 too quickly, and I would lose my final value. After all of that is now said and done, oh, additionally, similarly to another circuit in this project, we have to, this in the test bench is getting shifted left to account for the negative bits. So whenever you put in a 2, you have to put in a 4 in hardware. So this is just another example of being smarter than the code. Here we have a wave where this is gonna look a little crazy, but we basically have the state that we're in, the next state logic. So this is the state we're in, the next state, the state we're in, the next state, and so on and so forth. Here are the outputs. So as you can see, it updates here. This is our real output, and this is our imaginary output. And if you follow this right here, this is the sum out. So these are the values leaving the adder. So these are the values that are getting picked up by the registers here, and that's what's showing us our actual computation. There will be a photo of this in the, what's the word I'm looking for, in the report, so this can be more heavily looked at later. moving on to Quartus, we have the code, which I'm gonna briefly mention this. Because Quartus does not like negative buses, everything has to be moved to the positive, so 0 and higher. So it's nothing too crazy, but all of this just has to be 0 or higher. So again, being smarter than the code. This is what the block looks like. The block is a little crazy just because of all of the observations, but they are not used for actual test benching, so we're not super worried about it. Moving on to the test benching though. So we can see as you can see, I was fiddling with it a little bit, so I can set my reset high and just kill the whole thing. This is my start switch, so if I don't, sorry about that, if I don't hit that, then it does nothing, the state doesn't change. If I set it high, then as you can see, in the test bench, I was putting in decimal values of 2, but again, it's being shifted left 2, so we have to put in binary values of, we have to imagine there's a decimal point here, 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 and here, so just, again, thinking smarter than the code. So this will be the same example. So as you can see, it enters state 1, state 2, state 3, and then in state 4, it captures our first value. And then in moving forward, and then in the final step, it catches our final value. So there is a line here. I probably should have gotten a piece of paper to deviate between these two, but this is our 2 value, and I believe this would be a negative 36 because we're doing the complex with all 2s for this example. I'll probably put the equation in the report just so this makes a little more sense. And moving on to the oscilloscope, we can see that I did have to use human error again for the time delay. So about 2.34 seconds. And that should be everything for this circuit. Okay, and for our next circuit, we have a legacy subtractor, which is a sequential subtractor, where basically we have a 4-bit data in, we have our clock, restart, start, state. We are using a finite state machine for this, which is not very complicated. It's not really doing a whole lot. But what it is we have our RC, which is our internal control, our data sum. We have data sum is equal to data out minus data in, where the data out is the register value. And moving on, we have the step 1, step 2 parameters and internal signals for the states. And then we have the state register, just saying, if reset is low, then current state is next state, so on and so forth. And then we have the next state logic, so this is step 1, step 2. And then we have the output logic, which is just our control signals for the output. And as you can see here, if we look at a test bench of this, you can see that it goes from 0. And then our data in is 1, our data out is 0. And then once we subtract 1 from 0, it flips and it just keeps going. So nothing too crazy to look at. If we go here, this is what our RTL viewer is giving us. So we have our adder, selectors, and registers. That basically, this is what the compiler is thinking it needs to have in order to make it work. This is the block diagram in Quartus. And moving on to the hardware testing, if I go ahead and put this at restart, and then we run this down to 0. Now the Altera board is being kind of funny, so some of these LEDs are gonna light up whenever they shouldn't be. But what we'll see here is it'll go into state 2. Sorry, the button's kind of sticky. And you can see that there was nothing in it, and it subtracted 1 from nothing. Again, this is one of those random little LEDs that's lighting up for no good reason. And then we can subtract 1 again, and just continually do that, thus showing that it works. And if we move over to the oscilloscope, once again we have, since the internal clock for this is way too fast, I'm not using it. and due to limited time, I'm not making a system that can slow down the clock. So what I've done is I've done human delay. So we have about 2 seconds of human delay for this. And that pretty much wraps it up for this circuit. Hello, my name is Titus Dudden, and I'm here for project 3 of CpE 3110. For the first circuit that we're doing in this project, we are doing a fixed point add sub where we have a 4-bit data in, an 8-bit data out, clock, sub, RCE, reset, overflow, and some signed wires. Down here we can see that we have the assignment logic for the extension. Since this is signed, we have to take the MSB of data in and extend it so that it fits the wire. And then we have our subtractor adder logic, and then we have our overflow logic, followed by our register. And this one does not require a finite state machine, which the other projects will be requiring a finite state machine. For this in particular, the finite state machine was built into the test bench, which I will show off right now. This is the test bench here. So this will likely be included in the report since the all of the state logic is in here instead. So we have our wires, the parameter for the clock, our task, and then we have port forwarding, our clock generator, and then we have our apply test cases, which do the states for us, which is nice. And in this case, our register state control is controlled externally. Additionally, because this is fixed point, we have to be a little bit smarter than Verilog. So if I go back here, you'll see that this is -1 to 2, but Verilog does not really like negative numbers. So what we have to do instead is, if you saw on the test bench, we went from decimal, so real, to integer, and then we shifted it over 1. So what's happening here is we're putting in a 3, and it's coming out as a 6 because it's being shifted from the -1 to 0 and 1. So we're just gonna have to know that this actual value needs to be divided by 2. And as you can see, it increments all the way to 18, and then we flip the sub high, and then it starts going down to 0. It goes into the negative, and then, let me see, there we go. You can see that once this goes from a large negative number, while the subtractor is high, into a positive number, the overflow kicks. Moving over to Quartus, we can see that Quartus really does not like negative numbers, especially when it comes to buses. So what I had to do is I had to shift everything over into 0 and positive values. So the bit widths are the same. It's just, again, in this scenario, we're gonna have to be a little smarter than our code. It's up to us to interpret the data, not the program. This is what the block looks like, nothing too crazy. And if we, oh wait, let me show off the RTL as well. So this is the RTL here. It is a bunch of selectors followed by a register and some simple gate work, so nothing too crazy. Moving over here, we can see that on the hardware, I was fiddling with this a little bit earlier. Some of these green LEDs are gonna light up even though they're connected to nothing, so just know that the only one that is relevant is LED G0 here, all the way on the side. But if we, I believe, this will set the, this is our register, and this is our sub, this is the reset. So the reset's low, our register is high, so we can see this puts our data in. Now we kind of have to imagine that there is a little decimal point right here. So this would be 0.0, so this would be 3.0. So we just, again, have to be a little smarter than the hardware here. And you can see that, again, just ignore these green LEDs, they're lighting up for no good reason. But I can increment this, and then eventually we'll get to a state where the machine knows that it's about to overflow. So effectively saying that it's overflow. And then in the next state, we can see that it has overflown. And then moving on to the oscilloscope, we can see that it, again, I did not use the supplied clock. I had to use human error. So this has 400 milliseconds of human error. So relatively quick system comparatively to the other time delays that will be shown in this project. And that is everything for this circuit. Okay, for this circuit, we have a sequential twos component, twos complement, where basically we're taking a 10-bit input, and then we're gonna have a 10-bit output. We have a start, a reset, a clock, our state for observation, a finish for observation, so we know it's done, and a bit step for knowing which bit it's actually seen, and then the rotate out. These are all for observation. We have our control enables for, hold on, give me a sec. Control enables for our, goodness, I'm struggling here. We have our control enables for the registers, the flip flag, the bit count, the rotate out, and then we have our steps for the FSM, and then the current state, next state, and then we have our assignments, which are used to determine what the operational logic is happening. So we have a mux, where it's saying that if it's 0, it's taking the data in, else it's taking the rotate out, which is the data out from the rotation. We have the finish, which is saying that if the bit count hits this number, then we're done. The bit step, which is the number of bits we're on, and the rotate out. And then we have the register logic, and then we have the rotator logic, which is a little more complicated, where we have a reset and current state is 1, then it'll set everything low, so we don't get any weird uninitialized nonsense. And then it'll we have an if-else statement saying that if the step is 2, the rotate out is equal to the data in. And then if the current state is 3 and the bit count is less than the final amount of cycles that it should take to achieve this, then it'll say the bit count is this, add 1. And if the flip is low, it'll maintain the data that we have, and then once it finds the first, once it finds that the LSB and the data out and the MSB and the computational data are both 1, it will make the flip flag 1, and then the rotate out will then start flipping the bits, and then it will the rotate out will just equal the data out, or data out to rotate out once the finish flag goes high. Then we have the state register and the next state logic and the output logic. So the next state logic is saying that if reset is high, it's going to step 1, start, it goes to step 2, next state, step 3, and if it's during step 3, if the finish goes high, it goes to step 1, else the next state is step 3. And this is pretty much just to say that if we never get a 1, so say we put all zeros in, the finish will still go high and it'll still reset. And then this is the output logic for all of our states, just saying what's high and what's low. And we can go to a waveform here that shows this. So here we have a 4, and then you can see that this is the data out, this is the rotate out, so they're constantly going back and forth, and then the final data out is a -4, which is what we're looking for. We'll go over to Cordis, and I will show you the block first. So this is the block here where we have the data in, the start, reset, clock, all of our outputs, which these two that aren't being used are for observation, so I don't need them for the oscilloscope. But I have the data in being drug out here, and then the finish flag is what tells me the time delay, which unfortunately for this project, the time delay is going to be a human time delay because the clock for this is way too fast. And there's the code again, but if I go to the RTL viewer, this is where things get a little silly. So it has our current state and next state logic, or next state, current state, regardless. You have your combinational circuits here, And then it uses a string of just a ton of muxes over and over with registers to achieve the output, which looks very silly. Moving on to the hardware test. So we can see that our start is high. If I set the restart high, we can see that nothing ever runs. So if I drop the restart low, the start, so this would be 4, this is the same example. You can see that we are now in state 2, or sorry, state 1. So this is where our start is high. And then we'll go here, this is state 2 where the data has been loaded. And then we continue, you can see that it's rotating the bits. We can't see the rotate out for this. So we're only seeing the bits get rotated out. So then now it incremented the top bit, and there is a clock cycle between the rotate out and the data out. And then you can see right here, this green dot right here went high. This is our finish flag. So now we know that 20 cycles have gone through, and this is now -4, so it's working correctly. And if we move to the oscilloscope, you can see a time delay of 3.83 seconds, which is that human error. And that's everything for this circuit.